Okay, hi everyone. We are going to be talking about quantum effects and Bell's inequalities and their relationship to our models. And the question is whether there's a relationship between the last live stream I just did about a remote job submission and this. We shall see. One never knows what kinds of weird connections there are. All right, the primary thing we want to talk about is something that we had just tried to start on a previous meeting this week, which was looking at, so in this meeting we had been looking at double slit experiments and the possibility when you have of looking at, I think the main conclusion here was that we can, well, I mean, this was to do with the mapping of what are essentially spatial degrees of freedom onto quantum space and the question of how various wave functions relate. But I think we're really looking at a different, trying to remember what, okay, here we go. Here's what Jonathan had prepared previously about Bell's inequality. So do you want to walk through what you have here?
I can do, but it might make more sense to just redo some of the stuff because I think I now have a cleaner way of thinking about it.
Okay, fine. Let's do the cleaner thing.
The question is, do we want to start with the full Bell theorem, or do we want to start with things like Cauchy-Specker and Gleason's theorem and cases?
You have to remind me how all of these work, but let's start with the simpler ones. Let's start with whatever you think is conceptually most sensible.
Well, okay. I mean, okay. In a sense, I don't want to start with Gleason's theorem because I think it's kind of totally trivial in our models. I think Cauchy-Specker is the first non-trivial thing we can investigate.
Okay, let's look at Cauchy-Specker. But why don't you remind me what is Gleason's theorem?
So Gleason's theorem, okay, so mathematically what it's saying is if you consider the algebra, the C-star algebra of all bounded operators on Hilbert space, then that algebra is uniquely defined by the values on orthogonal projections as long as the dimension of the Hilbert space is greater than 2. And so an interpretation of that is you're saying that the state is completely determined as long as you know the answers to kind of all possible yes/no questions about the nature of that state. So it's it's a quantum information theoretic argument.
Okay, the state is determined by a collection of bits, basically, that represent results of yes/no measurements, effectively. Is that correct?
Yeah. Measurements in a loose sense. Yeah.
Well, projections.
They're orthogonal projections, which of course is not. That's a particular idealized case of a measurement.
Okay, so in our case, what does this correspond to?
I think it just corresponds to the question, to the point that you can define any state in the multi-way system by a yes/no question of, is it on this branch? Is it on that branch?
I see. So your claim is if we take your average multi-way system.
Yeah, I don't think this is a particularly interesting result, and I think it's kind of trivial by the nature of multi-way systems.
Well, I just want to walk through it just for a second. Mm-hmm. Okay, so you're saying that given a multi-way system, so if I say A goes to AA, for example, and I start off with the state just A, for instance, and I go 3 steps, I'm going to get some kind of tree-like thing. Whoops, and I make a states graph here. Oh, I need something like A goes to ABA here. Oh, I need A goes to AA as well. Then it'll make a big mess here. Okay. So you're saying that Gleason's theorem is talking about the states that come out here, right? These are quantum states. These are pure quantum states.
Mm-hmm.
And you're saying that, I don't quite understand the time evolution aspect of this.
Right, but I mean, so effectively each branch, for each edge here, you can ask a yes/no question, right? Of is the state at the end of this edge?
Well, except these edges have already happened. These edges up here have already happened.
Mm-hmm.
So normally,
but you don't know that. I mean, the statement that they've already happened assumes some reference frame.
Yeah, I understand. So let's imagine you've got a reference frame where this is the superposition that you're dealing with, this thing down here.
Mm-hmm. Yep.
So, and to say you determine the state is to say you determine the whole superposition. Is that correct?
Right, exactly.
Okay. So you're asking, does the superposition contain the state AAAA?
Mm-hmm.
And you're saying that if I project, what does it mean in this setup to project onto a certain... Well, you're saying that to make a reference frame in which you determine that this state is part of your story is to make a Brownshield black hole around that state.
Yeah,
right?
at some local level, yeah.
Okay, let's just walk through this again. I mean, so normally you're thrown a quantum state and you're told there are certain fiducial quantum states, which are these orthogonal projection states.
Yep.
And you are doing bras and kets with those states, and you're asking what are the values of those projections, which you might not be able to physically measure all of, but you're just saying mathematically, what are the values of those projections?
Right.
So what is the thing, if we're computing, this bra and another and a cat, I need to get rid of those things in the middle, but I don't know quite how that works. But if we're computing that projection, how do we actually do it here?
Well, that's what a completion is doing, right? It's that. So, the generic mantra, so to speak, is that if you're doing time evolution, then these are multi-way edges that point downwards that connect neighboring hypersurfaces together. Mm-hmm. But if you're doing measurements, and in particular if you're doing orthogonal projections, these are these are the horizontal multi-way edges. So if you have two states A and B and you want to project one onto the other, then it suffices just to have a completion step that maps A onto B, and then you see what the outcome of that is.
Let's be more specific. So let's say that in this projection, you're projecting onto the state AB, for example.
Yeah.
What are you proposing to actually do here?
Like I said, you take whatever state it is you're projecting, and then you add a completion step that maps that state onto AB, and then you evolve and you see what the resultant states are.
So in particular here, let's say we were going to do that with AB, okay? You're saying that we have a completion step. Let's say we have AAAA, and the completion is mapping that onto AB, for instance. Is that right?
Okay, that's a little bit funky because that's not a state in that superposition.
Okay, so you're saying you want to map it to a state that is in the superposition. So let's say ABAAA.
Right.
Okay. All right. So now we've added that completion, and now let's go another step.
Yep. And then we should see something occur.
Shall I go back and do this on a previous step? I think I'm going to do this on a previous step. Let's do AAA maps into AABA. And let's do just 3 steps there. Okay, now what am I seeing here?
Okay, so we now got AA. So now you can see the AABA. From AABA, there are new states that would not have existed if you hadn't added that completion step.
Okay.
And so those states that are now reachable from AABA, their superposition. So I mean, generically, when an actual orthogonal projection would have sufficiently many of these that you would end up with a single state, right? Because or you'd evolve the system for long enough that things had converged, and so the resultants.
Okay.
Then the resultant state would be the outcome of that projection.
Let's walk through this a little bit more carefully, okay. So you're saying this completion AAA. Okay, so you're saying add a completion. Okay, so we're trying to emulate. Okay, your basic claim is projection is like adding a completion. more specifically, so you're saying that the projection, I'm a little bit confused. So this is the projection which would project AAA to AABA is like adding that completion. But that projection will project other things, will also be a projection that applies to other things, right? In particular, AAA, the AAA will get, and I don't quite understand why that didn't show, why that step, I guess if I go another step, I'll see that do something, won't I? Better. Yeah, so AA, yeah, that then does a bunch of stuff.
Right.
Okay, so you're saying, back up here, could you walk me through this? So projection is like adding a completion. So we add the completion, AAA goes to AABA, right? Now what? What exactly am I supposed to see here?
Like I said, if you then evolve the system, there will be new states in the multi-way system that were not previously accessible.
Fine.
And so those correspond to the outcomes of that projection. And so generically, your projection will be, there will be sufficiently many completion steps, and or you will evolve the system to a sufficient number of time steps that the outcome will be will be causally will be sufficiently causal invariant that there's a single state, which is then the outcome of that orthogonal projection.
Okay, so your claim, we should be able to explicitly see this, right? You say we have to do other completions, or this is sufficient?
Well, I don't know this particular case. I'm not sure whether this is a valid projection or not.
Okay, what does it take for something to be a valid projection?
Well, we know a minimal example is the canonical Knuth-Bendix completion would be a.
Okay, so let's take a look for this system. Okay, let's take a look at the Knuth-Bendix completion for this system. And we're going to get to Koch-Specker in a second. I just want to try to understand this better. Okay, so when we're going to start off from A, for example, do we have to say how many steps we want to go here, or can we just say, so, are we just doing this? Is this correct?
No, you want to do canonical Knuth-Bendix completion, which doesn't require an initial condition or a step count.
So I can just say this here?
Yep.
Or it's a separate function?
Well, you can do either.
Okay, so I say canonical Knuth-Bendix completion.
Yeah. And it will output something. There we go.
Okay.
Which is reasonably minimal.
Yep.
So this is telling us that a symmetric projection from AA onto ABA and vice versa is sufficient to guarantee causal invariance.
Fair enough. Okay, so now we add that in here. So this will give a causal invariant system.
Mm-hmm.
Dandy. Okay, so now what?
So now, because it's causal invariant, whereas before AA and ABA would have led to disparate things, there should now be a common state on which they converge, which looks like ABAA.
Okay.
And that should therefore be the outcome of that measurement.
Okay, so which measurement are we talking about now? The measurement, let's be specific about what measurement are we talking about?
I don't understand the question.
Okay. We have a system here. We're making a measurement. Mm-hmm. What measurement are we making?
We're making the projection, the standard projection measurement that corresponds to AA, ABA. AA projected onto ABA, or vice versa.
So in a standard sort of quantum thing, we're measuring the expectation value of what operator?
This projection, or this orthogonal projection operator.
Okay, so the goal is measuring expectation value of the operator which projects AA to ABA, mm-hmm. and vice versa in this particular case.
Right.
Okay. Okay, so, and we're measuring the expectation value of that in this system. Okay, so then what is the result of that?
Okay, so I didn't realize, yeah, that there's more stuff coming out, so it's actually a little bit more complicated. So in this particular case, I mean, we'd have to trace it, but
well, let's figure out what that. So this thing, we want the subgraph here. Where what do we want? We want the neighborhood graph of what are we actually trying to get? We want the neighborhood graph here, or the vertex out component. Am I right? Of what?
what are you trying to compute?
I don't know. I'm trying to compute the expectation value of this operator in the system.
Right, which would be the total out component of, well, it'd be a combination of the total out components of AA and ABA.
Okay, so let's ask for that. Okay, that's the one step out component. Maybe we can get the two step out component as well. Okay, what do we learn from this?
So there should be, okay, if we now looked at the out components for the uncompleted system.
Okay, let's do it.
Okay, so after one step, it's the same.
That's
so the
odd.
the system was apparently already causal invariant.
That could be true, but I'm still trying to understand the relationship to Gleason's theorem of this. Or should we go? I mean, is this not relevant? Do you think we should just go on to Cauchy-Becker? Because
I think it is. I think it's relevant, but as I say, I think it's trivial. I think it's the question. It's the point. The point that's being made is you can go through, if you want to identify what multi-way state you're on, you can go through every multi-way state and ask, are you on this multi-way state? Now that's a non-trivial theorem when you're talking about Hilbert spaces, but it's a trivial theorem when you're talking about multi-way systems.
Okay, when you say, are you on it, you're saying, I mean, in the usual formalism, you simply evaluate that projection operator and you see what it returns.
Mm-hmm.
Right? But
in the simplest case, yeah.
Yes, but I don't understand. The evaluation of that projection operator looks non-trivial here. I don't understand what the analog of evaluating that projection operator, the Bra-Ket projection operator is in this case.
Yeah, I mean, as I say, it's the construction of a branchial coordinate event horizon, and then the resultant completion that induces.
Okay, but we've got a projection. Normally, when you do a projection, you only have to give one side of the projection. You're saying, I'm projecting onto this state. You're saying, look at all possible states and project onto this state.
Mm-hmm.
Right? Whereas here, you're talking about a completion which has two sides to it.
Yeah, in the symmetric case, but not in the asymmetric case.
Well, so what you're defining is, in a direction in essentially branchial space, this completion is, in a sense, a geodesic direction in branchial space.
Right.
Right? And so the projection that you're describing here is a projection. I mean, if we look at your average piece of branchial space, okay, some object like this, right? You are defining, I mean, in the case of, in a spatial hypergraph, we could define a notion of projection, right? We could say, given a geodesic, we look at, well, it's not completely obvious how you do it, but let's just walk through that for a second.
I think it is. I mean, and I think it's exactly what we're doing here.
Okay.
Right? You have two geodesics. You project one onto the other. You're finding the shortest path distance from the end of one geodesic onto any point on the other.
Okay, but let's just.
Okay. Am I missing something?
No, I think that's basically correct. I just want to do it more carefully. Okay. Okay, projections. All right, so let's understand what happens in the trivial case of vectors. Okay. So let's say we've got let's be absolutely trivial, just so we make sure we understand what we're doing. Okay, so we've got two lines here. We've got a line of the form, this goes to, I don't know, 1, 2, and we've got another line where these are representing two vectors. Actually, we could make this an arrow. No, let's just make it a line, doesn't matter. 0, 0, 3, 5. That's a particularly stupid collection of lines for me to make, but okay, there we go. So let's actually make this okay, here are two lines. Okay, so these we can think of as so the projection of this line onto this line is the shortest path here. We drop a perpendicular to that line. So the projection is this partial line here that is from the shortest point on that line to this line, the shortest path point from the end of that line to this line, correct?
Yes.
Okay, so far completely trivial, right? Okay, the analogous thing in the case of geodesics in our system is, so let's make a spatial hypergraph just so we understand what we're doing here, and we're going to make so let's pick up, let's just find I really need a better way to just find these the trivial case of this. Hold on one second, let me just pick one up here. Okay, so your average, let's say, okay, so that's your average, spatial hypergraph. Okay, so the idea here is the notion of projection is we start from a node and we find the geodesic, we find some random geodesic from that node, and we find another geodesic, and then we ask for the, okay, so we're essentially making, let's just do it, just so we understand it, because then we're going to do it in branch shield space, which is going to be a little bit more exciting, right?
That's what we're doing now.
What?
That's what this procedure is. It's a projection in branch shield space.
Which procedure?
The procedure I just described. Never mind. I mean, if you want to, okay, we can do the find shortest path thing if you want.
Right, but then what we're going to see the direct analog here. That's the point. That's what I think is useful, right?
Right, which we've got.
Which we've already got, you claim, up here with the Knuth-Bendix thing.
Unless I'm missing something.
No, I think you're correct. Okay. I'm not as quick as you are at this. Okay, so let's just do it more slowly, because I'm not guaranteeing that that there isn't some bump here. Okay, so I want to make sure that we understand the bumps, right? And also that we understand the significance of the exponentiality of branch shield space as compared to these other things, and what implication that has for for this notion of projection and so on. So I mean, what we have here is okay. So here we would be picking. So we got some vertex list here. Let's say we call this GG. That's our graph. And now we'll pick. I don't know. Let's say highlight graph of GG, and let's say find shortest path in GG from node 1 to node 20. And then let's say path graph of that. Let's see if that works. Oh, for goodness sake, why did that not work? Oh, interesting, because actually this needs to be an undirected graph. Right, which is slightly interesting that has to be done that way. And I don't fully understand that. Okay, fine, it went into that little proboscis there. Okay, so what we now have is this, and then we have the second path that we're going to have from node 1 Oh, I wonder if node 1 is at the end of that proboscis to node 30, let's say. Oh gosh, we had all this.
No, that looks good.
Okay, but why don't we put styles in here so we know what we're doing here? Style red. Is that going to work? Ah, why does it do that? Well, unless...
Overlap.
What's that?
They might overlap.
They might overlap.
Oh, yeah, that's true.
Right. One of many problems we may run into. Okay.
Oh, so no, in which case we can do 20 to 1, 20 to 30.
Well, let's do this. Okay, that's better. Okay, so here we've got one geodesic is going off in this direction, the other geodesic is going off in this direction. Okay, so our goal now is to project from that geodesic onto this geodesic, right?
Right. So you take the endpoint and you do you map find shortest path across all vertices on the other geodesic, and then you find the shortest one of those.
Okay. All right. So let's do this. So we've got this find shortest path there. So actually, we've got just from 20, right? So we've got find shortest path on the second one, right? Which is a bunch of vertices. Okay. So there's a bunch of vertices. Okay. So now from 20, we need to find the shortest distance. So from each of these, we'd say find shortest path in GG from 20 to each of those, correct?
Right.
Okay, so what
actually,
that's saying...
the last one is boringly the most, yeah.
Right, so what that's saying is the projection from this, well, we don't know which way around it is. Here, let's just, to know which way around it is, let's label the nodes here. Oh, actually, we do know which way around it is. 30, well, yeah, 30 is green, so that's the 30 there. So 20, that's 20 there. Okay. So from 20, oh, actually, it's kind of obvious from this picture that that shortest path there, that the shortest path from 20 to this is, well, it's sort of obvious. It goes to there. Okay, so let's pick a different example. So let's say going from, I don't know, 20 to 40 and 20 to 30, let's say. I bet we're going to find the same thing here as it happens, which is kind of interesting. I mean, in other words, we could do the same thing in, yeah, okay, but anyway, we get the idea that basically we're dropping a perpendicular here. Let's just do this in this case again. So find shortest path of, let's say, 20 to 40. There's our path. And now we want find shortest path from 30 to each of these. And let's say length / add that.
Oh, interesting. It's the first. Oh, no.
Oops, what am I doing? Length, I meant / at. It is, in fact, the first in this case. So in other words, in this case, rather bizarrely, that is closest to this than it is closer to this than it is to any of these others.
So they're orthogonal, or they're as close to being orthogonal as they can be.
Yes, I think that's a fair statement. Yes. Okay, so
Or they go into opposite directions.
That's also possible, yeah.
Well, so, but normally for vectors, oh, I see, that's okay.
Direction.
Okay, so wait a minute. So one difference between this and ordinary vectors is that here the geodesics are going in only one direction.
It's only a difference because we made it a difference.
I know that. I know that. We could extend the geodesic in the other direction, but we'd have to have.
We just
have
need to
a meeting
intersect them in the middle instead of origin.
Yeah. Okay. Is that the geodesics are joined at their end. Okay. Okay, we've got a number of interesting comments on our live stream, including R4, who is commenting that this business about geodesics overlapping is not a local issue, but might persist in the scaling limit as with Liouville quantum gravity, and gives a reference here.
That's interesting because, I mean, I personally have conjectures about these overlappings between geodesics being related to tensor products of non-integer arity. So I'm wondering if that's...
This looks interesting. This looks like this is a very recent paper.
Mm-hmm. I know one of the authors.
Okay. Well, this looks quite interesting. Thank you.
Yeah, fun. We'll have a look through.
What is this concluding, though? What do they conclude the physical significance, though, of overlapping geodesics is? See, I have a feeling that it is less serious for us because effectively we have an equilibrium, sort of pseudo-randomness, so to speak, that arises, but I don't know. Oh, whoops, it came to the end. Help, are there conclusions at the end? There's a proof of something. What is it a proof of? Okay, let's look at the abstract for a second. We prove that for any metric which one can associate with the Liouville quantum gravity. What is a Liouville quantum gravity?
I don't know.
Okay. For gamma and the interval 0 to 2 satisfies certain its geodesics exhibit the following confluence property. For any fixed point.
Okay. It's the reduction of the Einstein equations to the Liouville's equation in 2 dimensions.
Oh, okay. Okay, so what is gamma?
I don't know. This is
So what is the Einstein equations in 2 dimensions?
Well, the Liouville equation. That's the point.
But the Liouville equation normally is an equation which has that's a phase, the same equation as one's talking about, PQ in phase space as being Liouville, satisfying the Liouville equation. Is that right?
Right.
I see. So R4 here, that's a terrific handle. Okay, I get it. Okay, so basically these in this world, these are random planar graphs, and so the point being.
So what is gamma? Did you figure it out?
No.
Okay.
Gamma equals the strength of a conformal field on the random surface, is what R4 says. So the claim here is that 2 geodesics starting from the same point will always overlap in the initial segment. I don't know why that's the case. I mean, they will have finite probability of overlapping the initial segment, which is hardly surprising if they start from a single node. There are a limited number of places they can go. Yeah, I'm a little bit confused by this, but okay, interesting. All right, so you're making a connection between the LQG metric here, which of course is not loop quantum gravity, but is this 2-dimensional quantum gravity, and a Hausdorff dimension. Okay.
Right,
Okay.
right. Which is the point I was making. So I mean, there's not in conventional geometry, there isn't a well-defined notion of a non-integer topological dimension, because of course the number of orthonormal spanning vectors is always an integer. But if your spanning vectors are allowed to overlap, they can still be orthonormal whilst kind of whilst introducing a level of redundancy. So it potentially allows you to introduce some rigorous notion of a non-integer topological dimension by having a spanning set of non-integer size.
I understand. Because there is initial overlap, it is not the case. Okay, so this is
right. So I'm wondering if that's what this paper is saying, but having
some real time. Okay, I mean, I think I understand a little bit about the type of thing that this is coming from. Interesting. Okay, all right, thank you. We are, by the way, trying to collect make a complete collection of all sort of relevant papers to what we're doing that we can put on the website with some annotation to help people who are working on sort of follow-ons to what we're doing, to find relevant literature. Okay. So, all right. So anyway, we have this idea of projection of one geodesic onto another. Okay. Now, you're going to explain to me, in the multi-way system, we presumably have the same idea. That is,
which is
up here. Okay. Just a minute. We're okay.
In the spatial hypergraph case, you have a pair of geodesics, and you are constructing a new geodesic from the endpoint of one onto the closest point of the other.
Right. So let's just see that explicitly.
We just did see that explicitly, didn't we?
No, I mean in this here. What I'm asking for is
then in the multi-way system, any pair of states on a single hypersurface is also described by a pair of geodesics from the initial state.
Indeed.
Right. And so then we are constructing a new geodesic, i.e. an arrow that connects one to the other in order to construct the projection.
I understand. I think that's right. I'm just trying to be okay. So we've got this picture here. So we've got GGM or something as this. And now we say, let's indicate, I wonder whether this is going to work. Highlight graph of GGM. And then we want to say from A, shortest path from A to, let's say, AAA. Rather trivial shortest path here. In GGM from A to AAA. Let me just check that works. Find shortest path there from GGM should be that. Okay, terrific. It's that path there. Okay. So let's see if we can highlight that path. And let's see, find shortest path, and then we say path graph of that. How do we do this? Max, do you know how to do this? How do we actually do the highlighting here?
Well, there is some kind of custom style in there.
No, I understand that. I'm asking, how do I get this to work? I'm not saying why doesn't it work. I realize why it doesn't work.
I mean, why not use the structure?
Which structure?
As in the structure, the states graph structure, if you don't want to override the highlighting.
Sorry, I don't understand. I'm asking I just want to indicate this path, A to AA to AAA.
I understand. So why don't you use the states graph structure so you don't override the highlighting?
What do you mean by the states graph? Oh, I see. I get it. Well, yeah, okay. All right, okay. I understand what you're saying. So let's say, okay, so you're proposing that this be okay, terrific. And then we might say vertex labels are automatic. Is there a way of putting the vertex labels in the center? I don't know. Well, okay, there they go. Okay, fine. So now we're seeing that. So that's our first geodesic, so to speak. Okay, and our second geodesic was going to be the one that went from, what was the second thing we were going to do? We were doing AAA and ABA, I think. or ABAA. Okay, so the second one goes to, okay, so that one is style red. Oops. That thing there, styled red. And then we want the style of the other one. This one is going to be green, and that one is going to ABAA. Okay. So again, we've got this GD6, these GD6 that agree on their first leg, but then disagree. Okay, now we have the completion that says that now we're going to add a completion, and the completion was going to be somewhere up here.
Right. So the point is that the only sense in which this differs from the spatial hypergraph case is that now adding the third geodesic, which you have to do in order to drop this perpendicular, actually changes the dynamics of the system.
Okay, well, let's watch this happen. Okay, so this is now our third geodesic, is this thing here, right? That's our AA goes to ABA.
Well, no, if we want to do this particular projection, it would be AAA goes to ABAA.
I'm confused. I'm sorry. This is the canonical bendix completion for that multi-way system.
Right, which is a different. So that's enacting a different projection from the one that you're highlighting.
Okay, so you're asking if I project. Let's go, for example, here to let's project onto ABABAA.
Are you sure? But it seems to still be able to match one step to the other. Because if you take the first two A's,
ABABAA.
Right, but it'll match other things that wouldn't otherwise match. It's a different projection.
oh yeah, I see.
Now I'm really confused. Oh, I see. That's going to this one there. So these are two. So just so I understand, I could have, and I don't know whether I can have them at different. I don't see why I can't have them at different time steps. There's nothing special about these time steps. It's just a cosmological rest frame.
Well, as long as you're maintaining multi-way invariance, in other words, as long as you're not exceeding the maximum entanglement rate in constructing that foliation, then you're okay. Right? They are at the same. If you do that that projection, you're saying that they are at the same time step from your.
Fair enough. Okay, from your point of view. Okay, so let's go. Let's just go out to a. What was that one there? I just want to find one that has a different. I can't type that. ABABAB, ABAB, ABA. All right, there we go. So now here are two GD6. Okay, so now you're saying that the projection of one of these GD6 onto the other is what? In the directed graph, what are you saying we do?
We do a completion
of AAA corresponding to this.
Right, which is constructing the third geodesic in exactly the same way as we did in the hypergraph case that connects AAA to ABA.
Right, except in the hypergraph case, it was a naturally occurring geodesic. In this case, we're adding a completion.
Yes, right. That's what I was saying. So the only sense in which this differs conceptually from the hypergraph case is that in the hypergraph you can add as many geodesics as you want, and it doesn't change any of the dynamics. Whereas, of course, in the multi-way system, adding geodesics does change the dynamics.
But I mean, there is a sense in which there could be another geodesic that goes.
Not if those states correspond to unresolved or non-resolving branch pairs.
I understand, but in a causal invariant system,
if they correspond to resolving branch pairs, then we have a classical system, and quantum projection doesn't make any sense anyway.
Okay, let's walk through this a little bit more slowly, okay? So the point is, if this was causal invariant, if the original system was causal invariant, this will eventually these two things will eventually converge, will resolve to something. They will have a common future successor. Okay, what is the significance of that future successor in terms of your geodesic projection idea?
Well, it's saying that those geodesics eventually converge, so they're not actually distinct. They are the same vector. In other words, their projection is trivial.
Okay, so you're claiming that in a causal invariant system, all geodesic
vector onto any other vector, you get one. Or in other words, all of your, in your Hilbert space, all your quantum probabilities end up being one. In other words, you have a classical system.
Well, hold on a second. I mean, which is another way of saying that causal invariance implies this sort of quantum objectivity idea, because in the end, everything resolves. Even though it looked quantum for a while, in the end, it will all resolve.
Right. It's saying that, as we know, causal invariance implies in some continuum limit that you get classical physics.
Okay, let's be a little bit more precise about this. I mean, what that's saying is that in the end, right, and there's something one also expects in ordinary quantum mechanics, that in the end, things sort of in the end, in the limit, there's classical physics. But in this case, I'm trying to understand, okay, for example.
Yeah, I mean, so causal, we know that causal invariance implies classical physics, right? So the quantum mechanical case is the non-causal invariant case.
Well, look, you have the perception of quantum mechanics. If you haven't waited for the resolution to happen at some long time in the future, you have all the apparatus of quantum mechanics telling you about superpositions of states and so on, because the superpositions of states are what you are observing on a quantum observation frame that hasn't waited for infinite time. You're very silent. I mean, I think the the concept that the observer does completions is that is in some sense a way of speeding up the inevitable. If the underlying system,
we don't know that it's inevitable.
Well, if it's causal invariant, it's inevitable.
If it's not causal invariant, we don't know that it is.
We don't know that it is. If it's not causal invariant, then the observer has to actually do the completions, which is your kind of idea for. You see, I think your idea for the interpretation of quantum mechanics applies even in the case of causal invariance, because it is telling you.
No, I agree.
Right? I mean, your idea doesn't matter. What it's relevant to is at some finite time, there is a particular quantum observation frame. You're not looking at the infinite future. So the infinite future.
Look, it's exactly the same as the apparent horizon versus event horizon story we were discussing yesterday. Because causal invariance is a limiting statement, we can never know, just as we can never algorithmically detect an event horizon, we can never algorithmically detect causal invariance, generically.
That's
so
true.
All we're saying is we have the notion of, something like an apparent horizon. You have apparent quantum mechanics, even in the case where you have causal invariance, but you're kind of like, you're arbitrarily close to being non-causal invariant.
Okay, let's see if we can make that correspondence more precise. Okay, so the notion of apparent quantum mechanics, to what extent, in the end, the whole universe is a great big black hole in the middle type thing, or at least in some, if it doesn't expand quickly enough, in the end, our galaxy ends up as just a big black hole in the middle type thing, and that is, I think, analogous. That is not a particularly useful statement about there's much going on in the universe before you reach the point where everything is a big black hole in the middle.
Right. In any finite time, you can't tell whether you're in a causal invariant system or a non-causal invariant one, because it's undecidable. So in essence,
right. But I want to
quantum mechanical universe and a classical but almost quantum mechanical universe will look the same.
Fair enough. But look, if the long time future, I'm trying to make the analogy between the classical case of causal graphs and the quantum case of these, multi-way causal graphs, and
Well,
trying to understand.
It's graph theoretically, it's exactly the same thing.
I understand, but I'm trying to understand the physics of, what we would say in the black hole case. We're saying in the end, everything is just, I'm trying to understand how, particularly when it comes to branchial black holes and the idea of maintaining qubits as branchial black holes, and how that relates to, how that relates to the classical physics case of a final, in other words, what we're saying is, in the end, it's all boring because in the classical case, it just all turns into a black hole. In the quantum case, in the end, it's all boring because it all resolves into a classical result. Okay? And I'm just trying to understand the analogy between these cases, and particularly when you're thinking about, okay, well, all right, but
I don't see what the issue is. I mean, so in the causal graph case, you're talking about future, to define an event horizon requires a notion of future null infinity. So you're asking about convergence of causal pairs, for want of a better word, in the infinite causal graph.
Yep.
And this is exactly the statement that an event horizon is a global property of space-time. And the same thing is going on in the multi-way system. What's the? I'm trying to. What is it that you're trying to understand? Is what I'm trying to understand.
I'm just trying to carefully draw out these analogies. So first point is, the claim is that causal invariance in a standard causal graph is a convergence. Well, okay. I'm just trying to make sure that I really understand what the analogy is between the geometry of what's going on in these multi-way graphs and what's going on in the spatial hypergraphs. And this idea of projection that you're saying, that we can think about operators and projections of operators in quantum mechanics case as we can think about projections of spatial geodesics in the space-time case. I'm trying to make sure I understand that analogy. And I'm trying to understand how in branchial space that might be an exponential dimensional space, what the implication of that is for these projections of geodesics. But perhaps we should go on to the Cauchy-Becker thing.
As I don't think the Gleason's thing is that interesting.
All right, okay, let's go on to Cauchy-Becker. Even though I feel like I'm more or less have understood what's going on here, but I'm not sure I totally understand.
We can come back to it, but I don't know.
Okay.
I feel like we should talk about Bell's theorem at some point.
Let's do it. Let's do it. Okay, Cauchy-Becker. All right, tell me your version of how to think about Cauchy-Becker in this. I mean, first of all, I'm trying to remember there's the full Cauchy-Becker theorem is usually in terms of 20 or something different sort of measurements that you make, and between them you have to have certain consistency conditions in order that you are, that you're talking about a quantum space rather than a classical one. So how should I think? How should I think about that in this context?
Okay, so I mean, so just to remind people, sort of, mathematically, what the Cauchy-Becker theorem is really saying is, you take this algebra of bounded operators on some Hilbert space, and then you define this notion of a valuation of elements of that algebra. So so the valuation is a function from those bounded operators onto the real numbers that satisfies certain conditions. And then the Cauchy-Becker theorem says that if the dimension of your Hilbert space is greater than 2, then no such valuations exist. In other words, you can't. What it's basically saying is, this is this notion of quantum contextuality, right? The idea that you can't just assign predefined values to all of your observables. So whereas Bell's theorem is establishing that any effectively any hidden variable theory in quantum mechanics would have to have non-locality. Cauchy-Becker is establishing kind of the complement of that, which is saying that any such theory would also have to have contextuality. So you can't do this valuation procedure. So a concise way of saying that is that you can't assign values to all physical observables in your Hilbert space or in the algebra of bounded operators whilst simultaneously preserving all of their functional relations. So of course that has an immediate interpretation in the context of multi-way systems, which I say I think is relatively straightforward but non-trivial, which is that you can't collapse the multi-way evolution graph whilst still preserving all of the causal connections between the different branches.
Okay, that's an interesting claim. All right, so let's take a look at our average multi-way graph. Here's one. Okay, so you're saying that, but when you say collapse the branches, you mean by completions or what?
Yeah, but I mean, sure. That's the most general way of doing it. So my point is, I think what the Cauchy-Specker theorem is really saying is if we take the multi-way causal graph of the uncompleted case and we take the multi-way causal graph of the completed case where everything is effectively collapsed, right? The completed case is that's the situation in which you have purely classical physics, right? Everything has been valued. You've assigned a valuation to all of your bounded operators, right?
Yes, I understand. I would like to see that more operationally, but I understand the idea.
Right, and right. So then that's saying that in the process of doing that, if you started from a genuinely quantum mechanical system, whatever that means, whether that's genuinely quantum mechanical or apparently quantum mechanical, it kind of doesn't matter. If you do that, then the branchial edge, the branchial causal edges, which are the essence of those are the essential functional relations between your quantum states, must have changed.
All right. So in particular, this would mean that the multi-way system, the multi-way causal graph here, actually, well, okay. So you're claiming, if I say causal graph here, get some big mess. You're claiming that these causal edges, that if I do the completion, the causal edges must change. Is that what you're saying?
Right. And I'm wondering, I mean, we need to analyze this in more mathematical detail, but I'm wondering whether it's actually saying something a bit stronger, because I think that claim in itself is a bit, wimpy.
What is the, I'm sorry, what is the graph that has both events and
evolution causal graph?
Okay, let's just draw this in a way that we might understand it. Oh boy. Okay. So you're saying, so this is showing the causal relations between the events that connect these states.
Right.
And you're saying, were we to make a completion here that effectively gave us additional events, what is the complete? There's an event associated with the completion, presumably.
Yes, right. But I think what the Cauchy-Specker theorem would be saying is even if we subtracted out the events associated with the completion, the very act of having done the completion would mean that this causal graph is effectively is no longer isomorphic to what it was.
Okay.
You would necessarily add or subtract some causal edges.
By virtue of the fact, you say that you have done, I mean, there's several levels of interpretation here that I'm not completely getting, but we do a completion. So let's do a completion.
This is still, I mean, this is just my conjecture, but I think this is how it works.
Okay, maybe we should look at the little bit more kind of operationally at the Cauchy-Specker theorem. I think we had, didn't we have Mike's Ulray's stuff? Did we were going to.
It's somewhere in archive.
Here we go. Well, there's PDF here, but I thought we had a notebook version of this. I thought we had a notebook version that actually had the. Are
we planning to get Mike on a live stream, by the way?
I thought we were. I thought we were inviting him for this one, but
it'd be good to have him around. Yeah.
I mean, I thought that was what we were. I thought because he has an actual version of. mean, this is all of the complicated stuff.
I can't see any references to Cauchy-Specker.
Okay, he's doing the CHSH thing, which I
Yeah,
don't
right.
quite understand the relationship between that.
Well, no, CHSH is a bell type inequality. It's not a. It's about like I say, it's about non-locality rather than about contextuality. It's the complement case.
Okay, let me try to remember how this all works, because for one brief moment, I don't know whether it's let's take a look. It's a bad sign that I don't even mention it in the NKS book. We had a we've had some summer school projects about, because what I was interested in at some point was what is the minimal Cauchy-Specker, what's the minimum collection of observables that you need to establish, because this fact that you're claiming about Cauchy-Specker, there's an implementation of that in terms of doing a specific collection of measurements, right? But it's fairly complicated.
Mm-hmm.
And I don't know whether it's been simplified over the years, but it was like 21 measurements or something.
Okay.
And my question is, I'm trying to understand what that, and it says that there are certain inequalities that must be satisfied by a sort of true quantum system. When you make those measurements, there is no way to get, so I'm trying to understand what's the analogy to that here. What are the things that are analogous to? Can you re-explain your statement about what you think the Cauchy-Specker theorem is in terms of this? You're saying that basically it forces the causal graph.
Yeah, my point is just that those functional relations between quantum states that you're describing, right, these inequalities,
yes,
should be represented by branchial causal edges, branch-like causal edges, I think, right?
Well, you're saying, I think it would be useful to look back at, you're saying there are quantum states, and the Cauchy-Specker theorem is saying,
right, I mean, if they're quantum states and they're completely independent, there are no functional relations on them, then by definition, they're not causally connected.
Sure.
Right. As soon as they become interrelated, they become causally. There are features of one state that are causally dependent on the other state. So in particular, there should exist branch-like causal edges. And if the functional relations are preserved, those branch-like causal edges should be preserved.
Okay, hold on. So one thing we could do from these states is look at the branchial graph. That is, find out the entanglement of those states. What is the relationship between the Cauchy-Specker result and entanglements of states? I think what it's effectively saying is that there are patterns of entanglement that are impossible in some sense.
That would be one type of functional relation.
Which entanglement, or
no, the statement that effectively, if you have a particular configuration of states on one branch-like hypersurface, then you can't have another configuration of states on the same branch-like hypersurface, which is what you're referring to, would be one type of functional relation, but it's not the only kind.
Okay, but I'm just trying to understand. I mean, so for example, one statement might be, there is, by the nature of quantum mechanics, there are only certain graphs that can occur as branchial graphs, for example. And that's different. I mean, okay, what would a hidden variables theory or a contextual theory, or whatever you're calling it, what would it look like in terms of a multi-way graph?
Well, those are slightly different things. So a theory that violates non-contextuality would be one where there is just a single thread of history. I think that would be the simplest case.
All right, but let's take the example of a
right, because you're saying you could imagine you have a hypergraph that's evolving, and the multi-way system is trivial, so it just has a single thread of evolution history. But because of certain microscopic randomness details, it looks like it might correspond to a multi-way evolution if you're embedded inside it, right? And what the Cauchy-Specker theorem is saying is, no, that's actually not true, right? You can detect that you're not in a multi-way system.
Okay, well, let's talk about how. I mean,
because
given
the
that
functional relations are not preserved.
Okay, but wait a second. We're in a hypergraph, and we're in a string. We're just seeing, a particular sequence here of, we're seeing some sequence of strings produced. How can we tell that sequence of strings? So you're saying there does not exist, and this I can believe to be the case, there does not exist a rule. So here will be a possible version, okay, of possible version of is to say there is no string rewriting system that gives you a certain sequence of strings and nothing but those strings. In other words, if I were to get, let's say I want the sequence.
I really think that I think in order to have I think it really needs to talk about functional relations between states. It can't just talk about sequences of states.
Well, but this is already a reasonable problem to look at, which might give us some insight.
No,
right?
no, sure, but it's not I don't think it's the Cauchy-Becker theorem.
Okay, all right, fine. But so what this is asking is, if you live in a world where you see a sequence of strings, right? Could be a sequence of hypergraphs, doesn't matter. Does there exist a local rule? Okay, so the question is, i.e., does there exist a local rule, a finite local rule that gives you a given sequence? Or is it the case that that sequence must always be part of a multi-way system? See what I'm saying?
Yeah, I agree that that's part of the question, but it's a special case of this more general result.
All right, but let's try to understand the answer to this question. Okay, so in other words, if we look at all possible multi-way systems of a particular type, let's just go ahead and do that. Let's just look at all the multi-way systems. So consider all simple multi-way systems. Okay, then we're going to ask which ones have this property that they are in a sense classical, in the sense that they immediately give you just a single sequence of strings, right? So we can just do that. Where do we have our enumeration? Hold on, let me just pull that up. I'm looking for the enumeration function for multi-way. Let's see, enumerate substitution system rules. There it is. Oops. Okay, here we go. Okay, so this will give us all possible rules of this type. Okay, so let's start from the left-hand side here. Well, that's a rather boring case, but let's try this case here. Okay, so what we're going to do then is we're going to say this would then be multi-way system. Given the rule, let's say the first of the rule as the initial condition. Maybe we'll do this. And let's say 5 steps. Okay, so now let's map that over those. Okay, fine. So this is showing, I'm actually quite confused here. This is showing, in all of these, this is showing that there is a unique thread of history, although sometimes that thread dies. Right? So let's take as an example of something where I think that will not be what we find. I mean, actually, I'm pretty sure that if we even do, let's even start off with something that is something like AA, BAA here. Okay. I'm pretty sure we will already find that doesn't do this unique thread thing. Oops, what did I do wrong? Oops. Okay, so this does not do that anymore, right? This has no unique threads. This was a unique thread here, right? Because every successive thing there was just one of it, right? So that says that for these sequences, A, B, this sequence here, this is an example of a sequence which, if we observed that in our world, you know, then we would be perfectly happy saying that our world operated according to that rewrite rule, right? But if, on the other hand, we observe some sequence from this, there is no finite. Well, we conjecture is okay. So this is actually okay. So the point here is, actually, I'd never understood this idea. This is a good idea. This is a very clean and simple idea. I understand that it may have to be dressed up with causality and things later, but the simple idea here is, under what circumstances can there be a rule that has a certain kind of locality? In other words, a rule, it's kind of like in the Gödel's theorem case, you can't just go on adding axioms forever. A finite rule that potentially that has locality, right? A rule with a finite number of cases, for what sequences can one have a rule with a finite number of cases and finite size strings and limited size strings? Right? That's really the question here. And if the sequence you observe is one that is not of this type, then in a sense that is implying that you must live in a multi-way system, because you couldn't get this with a class of models of this type unless it was a branch of a multi-way system.
Of course. But my point is that you can't do that. You can't observe the string. In the same way as the hypergraph is not an observable object, the string is not an observable object. The only observable object to you as an observer is the causal network.
I understand.
So what has to be the case is that the causal graph for these things has to be fundamentally different from the causal graphs that you would observe for a multi-way evolution, which is why I stated the problem in the way that I did.
Yeah, I got it. I'm a little slower. Okay, so my point here is, okay, we got a stack of different issues. So this one is easy to understand. The next case up is to look not at the sequence of strings, but at the multi-way graph generated by this. And I agree, that's ultimately the case of relevance to the physics problem, right? But we can get some intuition about what's going on from this case here, where essentially we're saying, could this ever be a single branch rule? See, what I like about this is already sounding very Bell's inequality like. We've got choices. We can say, oh, we don't have to have a limited size string in the rewrite rule. Okay, we don't have to have locality effectively in the rewrite rule. Oh, okay, we can have something where you're always changing the rules that you're using as over time, which I bet is not a case that is considered explicitly in the Bell's inequality. Is it? Is there an analog of that in the Bell's inequality kind of setup?
Well, you're changing the rule in the sense that you're adding completion steps every time you change the detector settings, but that's not the way it's conventionally formulated.
No, I understand, but I'm asking in
conventional formalism, as far as I know, that's not a thing that's generally considered.
Although you probably could consider it. You probably could say, every time you do the measurement, you're actually doing a different measurement or something. And you have an infinite supply of different kinds of detectors, and that might be another way around it, which nobody ever considered because it seems too crazy.
Right. Or you could even do a very direct translation and say, you're trying to construct a classical hidden variable theory, but you have to keep adding dynamical laws in order to make sense of the observations you make.
Exactly. Right. Okay, so this is, in my opinion, is actually a very elegant way of understanding this issue, of understanding why you might be able to have such a conclusion, right? And I understand that you have to go to the causal case and then to the hypergraph case to really see it. But let's just analyze this case for a minute, okay? And try to see what is the condition on an underlying rule. So the question is, for what underlying rules and initial conditions do you have a unique thread of history? Okay, and those are the ones which have this property that, okay, actually that's not quite right. So that's one way round. Then the other way round is you could have something where there is one of these and there exists a threading through the possible different states here. That's one answer is, oh, it could be a multi-way system, right? So given that you observe a sequence, what substitution systems are consistent with that sequence? So as a matter of fact, we can probably figure that out from the sequence itself. I mean, one way we can do it is to just enumerate possible multi-way systems and look at their possible sequences. Another thing we can do, okay, let's just do that for a second, okay? Let's just do that. So we've got, this is our case for, so I don't know what kinds of multi-way systems we want to look at, but let's say we look at 2 goes to 3, I don't know, 3 goes to 2. I don't know how many systems there are there. Okay, decent number. And let's just look at AA. It's probably going to, well, let's look at AB. It might have more structure. We want to start with a unique thread of history, I mean, a unique initial condition. Okay, so then we're going to take, so this is all rules, is that. And then we're going to say, let's just start with AB. Okay, so now we want to do, oh, what the heck, let's do AAB. I'll probably regret this, but we'll do it anyway. Okay, so now this is telling us for every one of those rules what its sort of behavior is. So now, oh, this is kind of interesting. So a lot of them actually are unique, some are not. Okay, so then this is for every rule, we can look at its essentially signature by asking for the lengths of those multi-way steps for each of those rules. And let's, for the hell of it, let's just say, given the rule, let's go give that result there. Okay, so some of these rules give unique histories. Like that rule gives a unique history. These ones here are genuinely multi-way histories. Okay, so the next question is, given a sequence of strings, which is that consistent with? Okay, so we've got a sequence of strings. Let me see. How would we want to do this? So at a given step, we would ask, I see, we're asking what, we can think of this as a transition graph from a given state, a given string to another string. In each of these, we're okay. So I claim, let me think about this for a second. I claim we have a certain set of transitions here. Okay, so here's what we might want to do. So given each of these, I'm going to pick just, let's pick that one there. Max, I'm counting on you at least to come up with, there's about to be some non-trivial piece of code that's needed here. Okay, so we got that sequence of strings there. Okay, so what we're looking for, this thing here, what we want is every string in this, does this correspond to one of these? No, it isn't necessarily a states graph. We're just saying there is a sequence, right? There are many sequences consistent with that. I believe it's the same thing.
Oh, all paths in the states graph, isn't it?
Yeah, of course.
Right. Right. So I mean, this thing here.
Well, strictly not the states graph, strictly the evolution graph, but in this particular case, they're the same.
Okay, so we've got the evolution graph, and we're asking. No, it's not quite right. It's not quite right for what we want, because this is saying ABB is a dead end here, right? The rules no longer apply to ABB. But we don't know that. We're just observing some sequence of strings here, right?
Yeah.
And so then our question is that sequence of strings consistent
with the evolution graph?
Well, for this case, yes. But the question is, does there exist a set of rewrite rules which will give just that sequence and nothing else? Right? That's the case, right? That's the case where there's
a single unambiguous thread.
That's correct. But I mean,
it might be 2 questions. Yeah.
I am asking 2 questions. What I'm asking is, if I give you, okay, let's just look. Okay, just hold on a second. If I take string tuples, AB, 4, for example, okay? Now, what I might do, I'm trying to just make up a sequence that I could look at, right?
Right. So the interesting algorithmic question is, can you design a set of rules that's obviously in this particular case, because they're all a fixed length, you can easily effectively you can map rule onto this in such a way that, first goes to second goes to third, and so on.
Yeah.
And that will give you a maximal set of rules that will be of length, the length of this minus 1.
Well, you're saying,
and the question is there a rule set that is smaller than the maximal than the length of the sequence minus 1 that is consistent? It's an algorithmic information question. You're effectively asking, you're asking for the Kolmogorov complexity under the constraint that you don't have to define an evaluation order.
You could think about it that way, but
if they're not the same length, then even if you do that, you might get other stuff as well.
Right,
exactly.
But then the evaluation order becomes an issue.
Right, but the point here, okay, so look, what one possibility is, as you say, something like this, right? That would be a possible, that is a set of rules that will generate, right? If I say multi-way system, just to be explicit, right? If I say multi-way system of that set of rules, and then I say AAAA, let's say whatever this is, 16 or something, let's say 20, just because I want to see what happens. Okay, then this is a model, a very bad Kolmogorov complexity model for that sequence, right? But it works, right? And it is unique. But the question is, now if I change that sequence, I'm confused how to do this. You see the problem, that if I change the sequence, okay, let me do something much simpler. Let's say that I have the sequence AA goes to AB, help me out here. I mean, so I've got something where I'm saying, let's say AB goes to AAA, AAA goes to ABA,
right, and you already have the evaluation order problem.
Okay, well let's watch what this actually does. Okay, so this would be the sequence. So now I'm starting from AA, I'm starting from the sequence. My observed sequence is AA, AB, AAA, ABA. That's my observed sequence.
Right, but now it's going to bifurcate at the second step.
Okay, hold on. So then what I'm going to do is I'm going to take my observed sequence. I'm going to say, feed that into a multi-way system. Feed that in as the rules of a multi-way system. Okay, great example, right?
Yeah.
So now the question is, okay, so next question, do there exist rules that will generate that observed sequence that do not lead to a bifurcation?
I think not, because you have to, okay, so in order to get from one state to another one, you either have to have the rule as we just made, or more general rules.
Right, right.
Well, you're saying, why is it the case that you have to have a complete state to complete state rule? Because you might not have to have that.
Because if you have part of the state to another part of the state, complete state to complete, I mean, it could.
No, isn't that an overlap question, like unification and so on? Whether there exists a substate that will be, I mean, so, okay, so go ahead.
If you have the rule that goes from part of the state to another part of the state, the rule, the rule that gets entire state would apply as well. Because it just preserves other parts of the state.
Right. The point is the only places where you need a rule that applies to part of the state is precisely the case in which you get an overlap. Otherwise, as Max says, you can just simulate the rule that applies to part of the state with the rule that applies to the whole state.
No, but then you may be able to get, the whole point is you're trying to limit the number of possible rules you have to use. So you're saying, but I think it's an overlap condition thing, like the ones that we use for causal invariance, that says there might be a rule, but it only applies in one place. And the states that you generate will keep it only applying in one place. Therefore, even though it's a sub-state rule, it doesn't have multiple applications. It only has one application. Look, it's the same thing in a multi-way graph. If a given state has only one event coming out of it, I mean, I think this is going to be, okay, so I think the result is going to wind up being, as soon as you have multiple events coming out of a single state, you have this ambiguity. So in your causal graph case, I think that's going to end up, let's see. Well, okay, first point is, given an observed sequence, for some observed sequences, there exists a purely, okay, for what observed sequences does there exist an unambiguous rule? Okay, that's the question to ask. A rule that doesn't lead to ambiguity or lead to branching. Okay, so for example, one that we did earlier. Okay, if I see if my observed sequence is, here, let's just do it.
So ambiguity appears when the rule which we used for the entire state applies to a part of the state somewhere else. So in particular, if all the states have the same length, then there would never be an ambiguity.
Okay, but look, in this case, if my observed sequence, if my observation is A, AA, AAA, quadruple A, etc., then I'm great. Then there is a model that does not force multiwayism. See what I'm saying? there is a classical model in effect of this dynamics.
Yeah. I think we all understand.
Okay.
So yeah, as Max says,
that's because there is one character on the left.
Okay, so what do you think the condition is? So what's okay? Do you believe it to be the case? For what observed sequences does there exist a rule that doesn't lead to branching? What do you think?
Well, as Max said, a trivial one is that they all have the same length.
Okay.
A less trivial one is they have different lengths, but the characters on the right do not. On the rights of the rules don't overlap. With
okay. So case one for quotes for single threadedness. For single threadedness being possible. Okay. Okay, single threadedness can occur. Threadedness is possible when?
Well, the left sides don't overlap. That's one case.
What do you mean by left sides? There are no left sides. All we've got is an observed sequence. All we've got is this observed sequence. And I'm simply asking you, for what observed sequences is it the case that I can construct essentially this classical rule?
Well, the left side would be everything except for the last element.
So you're claiming that it's possible when there is no overlap. What are you saying? There's no overlap between the sequences
strings except for the last element.
Okay, I don't really understand.
Because that would produce non-overlapping system of rules.
Okay, so you're saying there's no overlap between strings except for the last element. So, and that will limit the length of the strings, because as the strings get long enough, they'll be forced to have overlaps.
For a finite character set.
Yes. Okay, so
yeah, and that's distinct from everything has the same length.
Right. The everything is the same length is the trivial case.
And why is everything is the same length? Because when everything is the same length, the maximum length of the sequence is the tuples, right?
What does that have to do with it?
Because, okay, given a finite character set and given a given length, k, n, if there are k characters in the character set, there's only k to the n strings that are allowed.
Yeah, but finiteness of the sequence doesn't imply finiteness of the rule. That's the whole point.
No, I understand, but look, if I take the
reason why it matters that they're all of the same length is because then there's no difference between a rule that applies to the whole state and a rule that applies locally.
I know, but there's an additional problem. There's an additional problem. Okay, I've got this sequence. Let's say I've got this, and I start making up a sequence here. Okay, I'm going to make up a sequence. I'm going to get this, and I'm going to start saying I want this next.
Caveat: you shouldn't have duplicates.
Okay, you've got another condition then.
Right.
I agree with you. There can't be duplicates.
Duplicates go to the same.
Right. So either the string is periodic for single threadedness, let's say ST, for ST equals single threadedness. To get the property ST, you must have no duplicates, because you can have duplicates in the multi-way case. If you're allowed ambiguity, you can have duplicates. Okay, you must have no duplicates unless the whole sequence is cyclic. Right? That's one condition.
The last part of the sequence. I mean, except for the prefix.
Yeah, okay. Unless the tail of the sequence. Okay. So no duplicates. All right. So that suggests that if you want to have a long sequence, then the sequence has to be of increasing size. right? Because otherwise you're going to run out of cases. All right. So then my question resumes: how do I know that this sequence, for example, a to the n, is capable of a single-threaded interpretation? For example, let's take the sequence. Okay, I'm going to take a particular sequence. I'm going to take the sequence AB. Let's say okay, my question is that a sequence for which there is a single-threaded rule?
Well, you'll need to apply this algorithm
B goes to BA.
This partitioning.
Jonathan, what are you saying?
B goes to BA, obviously.
Okay, fair enough. Okay, so for this example, in this case, there is an ST rule. Specifically, oops.
B goes to BA.
Okay, dandy. Okay, so that's an example of one that is classicalizable. Okay, so let me pick another one. Okay, let me ask about, for example, okay, so let's say I say, and there's going to be some kind of grammar of what's possible here. That one looks easy as well. That one can be done with the same trick. Okay, so these are two examples where they can be.
Actually, I don't think that can be done with the same trick. I don't think this has a straightforward.
All right,
rule.
so let's take a look at this one then. Okay, so okay, so is the following an ST rule? Okay, so how would we find this out? So
partition it into rules and see what happens.
no. I want a finite number of rules. I'm not going to have a number of rules that's equal to the length of the thing. That's not interesting. I want a number of rules like this case here, where even though we could go to an infinite number of steps, we have a very small rule that will apply. Yes, Richard on our live stream is saying it's almost the opposite of the pumping lemma. I agree. It's something like that.
Yeah, exactly.
But so that I was, I'm wondering about production rules and context-free grammars and what, under what circumstances does this, in a sense, our multi-way systems are like the applications of production rules. It's showing all possible applications of production rule. So this is saying, I mean, this might be related to unambiguous. I don't know. I mean, there's a whole theory of non-ambiguity of context-free grammars that might be at least a special case of this, which is, by the way, a rather complicated theory of for what context-free grammars is there an unambiguous parse, which is effectively what we're asking for here. I think maybe not. It's a related question. Okay, but let's see how we would answer this.
Do we know anything about the Myhill-Nerode theorem?
Yes, the Myhill-Nerode theorem is about non-deterministic finite automata going to deterministic finite automata. It says that there exists, for any non-deterministic finite automaton, there exists a perhaps exponentially bigger deterministic finite automaton.
Isn't that what we're dealing with?
Don't think so.
Why not? A branching multi-way system is a non-deterministic finite automaton.
let me think about that for a second. So in general,
But we're not emulating them.
okay, hold on a second. So normally, in the typical case of this, to show an example, let me see. The typical situation there is something like this one, where, okay, so these are, let's see, I have an example here. Oh, this might be relevant. Okay, so this is pointing out the correspondence between multi-way systems and formal languages. These are the regular languages, right? Where you're, in a sense, always extruding from the end of the string. Because a regular language is, you're going through a graph and you're always adding elements to the string. Whereas context-free, here, you are inserting in the middle of the string. If that makes sense.
Right. So obviously regularity is a sufficient but not necessary condition for single-threadedness.
Well, so the implication is, if it's a regular language, okay, so wait a minute. Yeah, okay, so you're saying if the sequence is as generated in a regular language, then there exists, this is related to this whole learning theory stuff, then there exists a DFA that will generate that sequence. That will be the claim. Not sure this is right. That's not right. It's not right because no, it's the wrong way around. The acceptor for a language, look, the DFA in a language, take a look at what they actually look like, okay? So, wherever it is. Okay, so when you make a language, okay, so these are some typical DFAs. Oh, come on. Let's see what happens if I just try and drag this here. Oh, that's really weird, but anyway, it worked. Okay, so these are typical DFAs. If you can see one of these guys.
Yeah.
So what happens is, this is either a generator or an acceptor for a language. Okay. So what happens here is that given a node, you are either able to put an A down there at this step. Well, this step, you had no choice. But at this step here, this is a DFA. So going out from that node, from that state, there's only a single edge that has an A on it and a single edge that has a B on it.
Mm-hmm.
Okay, but the problem is, you can get many different strings here. I mean, it's a perfectly good DFA. For example, the DFA that has, like this DFA here, okay, is that DFA there is a perfectly happy DFA which generates all possible sequences of A's and B's. So it's not helping us in our quest to find a multi-weighable system, this just generates all possible A's and B's, sequences of A's and B's. So I think it's not quite the same problem. I don't think this is right. I don't think it's right. I think it's a slightly different problem. So again, let's come back to the question, does there exist a multi-way system? So I think it's also more like a theorem proving thing, right? Maybe there's a way of using the theorem prover to do this. Because what you're trying to say, even that's not right. Okay. Does there exist a string rewriting system? Okay, so in this case, we were winners. There was an ST rule that generates this sequence. Okay, how do we determine if there is an ST rule that generates this sequence? So clearly, to go from here to here, so one question is, what rule? Yeah, I mean, I don't understand why we don't just figure this out. Look, to go from any one step to the next step, we know what rule can be applied, right? That's essentially that's like the, event decomposition function or something. That's saying what events can go from here to here. See what I'm saying? So what possible rules will take you from here to here?
Right, and then you compute an intersection across all of those for every pair.
Exactly. So let's just so that's what we have.
But that's an undecidable problem in general.
Okay, but let's do some cases of it. Okay, let's do some cases. What?
I think I have an idea. So
because we're going to get intuition about and
So okay, for the first two transitions, just use the entire state for the rules. And after that, have a rule which says BAA goes to BAAA.
Okay, well, hold
would only apply on the left.
You're trying to actually answer this, but we were trying to give a general algorithm which involves what moves, given two strings, this string and this string, what sequences, okay, so given those two strings, what, given that you're going from this to this, what are the possible decompositions of those two strings? What are the possible sub-rules that lead you to this? Does that make sense? Is that easy to answer? I mean, okay, so one sub-rule that leads you from that to that is A goes to AA.
Yeah. I mean, this is what diffs are.
Okay.
Isn't it?
More or less, but it's all possible there. For a given transition here, what rules are necessary to give that transition? Not that transition and no other transition. It's just that transition. What are the possible things that we can do to the left-hand side? So, two things that we can do that will lead to this, one is A goes to AA, and the other is the rather uninteresting whole gulp transition, okay? Because what we're going to
the simplest one is empty string goes to A.
Okay, fine. Okay, so the point is that most of these will give us something which rapidly leads to ambiguity. The theorem that we're trying to get is that and the way that the intuition we're trying to get is that it becomes that there isn't, for certain strings, it becomes impossible to have a classical theory that works for that string. That's basically what we're trying to get to here. We want to see how does the classical theory fail, and it forces you to have essentially a multi-way system to explain what you see. Right? And I think that's going to be generalized. Then we have to understand, once we've got that case, then we generalize to the causal graph case and see how it works in that case. I mean, Jonathan, do you think that that's silly?
I don't know. I wanted to talk about Bell's theorem, but we can do this.
No, but I think this is the essence of what's going on.
Except that I think you have to consider the functional relations for Cauchy-Becker.
But
I
look,
agree. This is an interesting problem. I think it's a special case of something that we can prove in a much more general context that's useful. But I mean, I don't know. We can.
no. Wait a second.
can
Wait a second. Wait. The challenge is in talking about all of these, inevitability of quantum mechanics theorems. Okay, they are traditionally quite complicated. That is, it's quite hard to get, an intuition around why in Bell's inequality, in Cauchy-Specker, by the time you've got 21 measurements you're making and you've got some complicated thing where you've got to prove some result, about C-star algebras and things, it is hard to have a simple-minded intuition about what's going on. What I'm excited about here, because I've never seen it before, is the simple-minded intuition. There exists some, set of observations, some sequence of things that simply does not have an interpretation in terms
classical
of
physics. Yes, but
right.
To make that correspondence, you have to talk about observable quantities and therefore causal connections. You can't just talk about evolution.
I know that, but this is a simpler case. It's a simpler case, right, where you can see I think the nub of the phenomenon, which I had not understood before. I mean, that is the nub of the phenomenon that, given a finite set of rules, there might be an observation which can only come in a family of observations that cannot exist on its own, right? To me, that seems like the intuition that's behind all of these results. Now, okay, I want to solve this actual problem, but let's go back and understand your statement about causal graphs. So, I mean, you're saying what? I mean, you think that there is a general. First of all, there's probably a general result about these strings. Okay, there's almost certainly a general result.
Sure.
But what do you think? What kind of a result is it going to be? I mean, in other words, for a particular sequence of strings, there either will or will not be a single-threaded rule. And eventually, the set of strings for which there is a single-threaded rule will be essentially a set, you won't be able to get, because the number of rules is small compared to the number of sequences, given that you have a limit on the size of the rule and so on. Quickly, you will find many sequences for which there is no rule, right? This is clear. And then the question is the sequence that corresponds to actual quantum mechanics one for which there can be no such rule? And what characteristic does the sequence that corresponds to actual quantum mechanics have that prevents it from being one of the ones that has a single-threaded rule? Now, maybe you're going to answer that by looking at causal graphs. Do you think you are?
That was the plan.
Okay, but so
I mean, because my point. Okay,
yeah, go ahead.
I mean, this is just an algorithmic randomness test. That you're placing an algorithmic randomness bound on string sequences, which is a perfectly interesting thing to do. I just don't think it's directly relevant.
No, look. No, that's not right. That's not the only thing that's going on. No.
Is it not the case that you by saying you can't have multi-way systems, you're putting a computability limit on the rules? Is that not the case?
Yes, but the interesting point here is
so the question is
no. Look. Given a sequence here, it is pretty obvious that it is very obvious that there are many sequences for which there is not a simple. I mean, you're boxing it. There are three stages here. You can't, and I just hadn't understood these three stages before. Okay, you can't do it in such a way that it's single-threaded.
Mm-hmm.
Then, at some point, you can't do it at all. Right? Even if it's multi-way and everything, you're going to run out of, the number of sequences is large compared to the number of possible rules.
Right. That's a higher algorithmic randomness bound.
That's not 100% obvious. Okay. In fact, it isn't even true. Look, let me show you. So look. Given this sequence, given this multi-way system,
you can generate all possible sequences of A's and B's.
Right. So it in fact isn't true that. So in fact, what's the case is that,
or at least ones that grow one at a, one letter at a time.
Indeed, but we could avoid that as well by having in there an A goes to blank, B goes to blank. So then we could generate everything. Right. So if I just add.
Yeah, as long as step numbers don't matter.
Well, it can only change by one. I mean, there's a speed of light. It can only change by one symbol at a time. I mean, by one. It can only change in length by one symbol at a time. Actually, it can only change by one symbol at a time.
Right. Right.
So there may even be sequences. Okay, so there's a hierarchy. There's sequences that can be generated in a single-threaded way. There's sequences that I suspect can't be generated at all by a finite collection of rules. At least in the limit, they obviously can't be. And there are sequences which can be generated, but only as one of a member of a multi-way family. Right? Okay, so the claim is that in physics, one is living in the intermediate case there.
Of course.
Right? So the question is, okay, but it would be nice to understand, to get a feeling for when that intermediate case, how common, is that a thick intermediate case or is that a thin intermediate case between this single-threadedness and you can't do it at all? I think that's a useful piece of intuition, but okay, we can put that aside for now. Okay, let's come back to okay, so then your point is, this is looking at what happens, a sequence in the multi-way system. But you're saying what is observable is the causal graph associated with this, right?
Mm-hmm.
Okay. So
which obviously has the advantage that it's not dependent upon string systems. It's a general property of any multi-way system.
Sure.
You're saying that there are some combinatorial structures, independent of whether you're dealing with string systems or Wolfram model systems, whatever, that are either non-computable by multi-way systems, or there are some causal structures that are computable but only by multi-way systems of certain types. So you can place, a multi-way system as a universal model of computation. So if you place certain restrictions on it, like it can only have a single thread, it restricts the classes of computations you can do. And so some causal graphs will be non-computable with some other models of computation.
Right. Okay. So your statement there is, consider the causal graph or multi-way causal graph generated by a multi-way system and ask the question. I mean, okay, that's a perfectly reasonable question, not unlike this question, actually. I think it's a more complicated version of this question. The question is, what multi-way graph, what causal graphs, what possible structures of causal graphs can be generated by multi-way systems with certain characteristics, like finite size rules?
Exactly. So it's more general, not system specific, and relevant to physics, I think.
Okay, but okay, so all right, let's look at, okay, so causal graph case. So the question is, what structures of causal graphs can be generated by, well, there's really two, it's the same story again, because what it is there are causal graphs which are one-shot causal graphs. There's no multi-way system. It's just a single thread of history. Right? And there's a causal graph associated with that single thread of history.
Mm-hmm.
Okay, so the issue is, what structures of causal graphs can be generated in single-threaded systems versus can be generated as part of multi-way as part of multi-way causal graphs?
Right. Or in other words, I show you a graph is there a general procedure by which you can determine whether it was generated by substitution system causal graph or by multi-way system?
Yes. Or by, or well, in
or Wolfram
particular,
Model causal graph or whatever.
No, I understand, but where it is in the case of causal invariance, all the causal graphs for the multi-way causal graph are ultimately the same. So the question is, if I exhibit, and I think the causal invariance case may be, well, okay, so given a finite causal graph, that might not be the same yet. You can ask the question, is there a single threaded system that could generate that causal graph, or must this causal graph only come from a multi-way system, right?
Right.
Okay, which I claim is a similar but more complicated example of the strings question.
No, sure. I mean, yeah, they're obviously related. It's just that, yeah.
Okay. So let's imagine. Okay, so let's say we have a result. So there will clearly be a result that says that for the vast majority, it will be easier to generate causal graphs that are. It's not so obvious when there's causal invariance. Not so obvious to me that isn't a pretty big constraint on what causal graphs can be generated. Is that obvious to you?
No. I mean, I agree. It is a big constraint.
Okay.
I mean, obviously, it's not as big a constraint as a single thread of history, but it's a bigger constraint than unconstraining.
Right. So the question then is, for these systems, if we look at all possible graphs, in the space of all possible graphs, which graphs can arise? Same question, really, as in the space of all possible sequences, which sequences can arise? Space of all possible graphs, which graphs can arise? And it would be very useful to relate. I don't know whether it's Cauchy-Specker, CHSH, Bell, whatever. What is the closest approach of that question to something which is formulated in the standard way in
Well, yeah, I mean, that's what I was trying to say at the beginning. I think this is the Cauchy-Specker thing.
Okay.
Because
try it again, because I was too dense to understand the first time around. Go ahead, try it
right.
again.
So as I say, the Cauchy-Specker theorem mathematically is saying that there doesn't exist a valuation of all operators that preserves functional relations. Right.
Okay.
So evaluation. So enforcing evaluation upon all operators is the analog of taking your multi-way system and collapsing it down to a single thread.
I understand that claim. Yep.
And so,
I mean, in the sense that an operator is an event in the multi-way system.
Right. And so what you're saying is you can't do that without inevitably changing the causal graph, or to put it in a more general sense, that single-threaded time causal graphs have a fundamentally different structure, an identifiably different structure from multi-way causal graphs.
Okay. So let's try this again. And then the fact is that we can look at our models and we can ask the question, do our models give you causal graphs which are incompatible with the single-threaded interpretation?
Right, exactly.
Okay, so what do we think the condition is? For example, let's say, I mean, if we were to consider a model where there is a single-threaded interpretation, I wonder whether that has immediate implications. It certainly has implications to the structure of branch yield space, which is then degenerates to something trivial, right?
Right, single-pointed branch yield space.
Right. What implications does it have for the spatial hypergraph? I bet that has to be trivial as well. I bet that if there is there's no ambiguity that you can't have a spatial hypergraph that is, has anything like the structure of space.
I agree. The hypergraph sequences do seem more boring than the string sequences in that sense.
Well, maybe Max can see his way through this one. But I mean, in other words, the stack of things necessary. I mean, basically, the claim is ambiguity, which is what leads to quantum mechanics in our models. The issue is, how important is ambiguity? What does ambiguity lead to? And is it the case that the whole structure of physics depends on ambiguity? In other words, this is the question of the inevitability of quantum mechanics, right? As soon as you have a multi-way system, you have as soon as you have a non-trivial multi-way system, you have inevitability of quantum mechanics. But what this is asking is, given an observed sequence. Yeah, I mean, in other words, okay, you could have a situation where there is a single-threaded version. The multi-way system degenerates to a single thread. And the question is, what does that imply? I mean, it's very unnatural in our models for that to happen. But the question is, what completely falls apart if that happens? Okay, so what is wrong with single-threaded physics? Right? Then the branchial space is trivial. I mean, clearly, you don't have quantum mechanics, but what else do you not have? I mean, do you not have, can you still have time even in single-threaded physics?
But there's certainly meaningful time, right? Because the Wolfram model systems can simulate string systems.
Well, the time may be, I mean, is it always computationally reducible? Probably the answer is no, because I suspect you can emulate, a random complicated Turing machine or cellular automaton, even in a single. Okay, let's ask that question.
Yeah, our CA emulator is single-threaded.
Okay. So you can have universality. Right. You mean the 110 CA emulator?
Well, any CA emulator, including 110.
Yeah, right. But because by its nature, so you say, is that really the case that it is completely single-threaded? It doesn't require any additional constraints? Yeah, I think it is completely single-threaded. Okay, so it is possible to have non-trivial dynamics and be single-threaded.
Although the causal graphs in that case are completely trivial, but I don't think it's necessarily the case in general.
Okay, to have non-trivial dynamics and be single-threaded, e.g. CA emulator. Is the causal graph trivial? I thought it wasn't so trivial in that case.
No, it is trivial. It's just there's a particular structure that appear in different places of the special graph are different, but the structure of events is the same. The causal graphs are identical for every rule.
Oh, I see. Yeah, that's right. I mean, the causal graph doesn't depend on the rule. The causal graph, in this case, in the CA emulator, the causal graph is just showing the infrastructure of the emulator.
Although I think I need to clarify that it's single-threaded in the local multi-way system case. It's not single-threaded in the global multi-way system case because you can still apply events independently in different places.
Oh, you're right. You're right. I mean, if we draw, I mean, we could probably just do it explicitly, right? So that didn't work. That was supposed to be. Okay, so there's a Turing machine, for example. That's the ordinary causal graph for that Turing machine, right? By the way, notice that that isn't completely trivial. That depends on the actual dynamics of the Turing machine.
The Turing machines ones are not trivial.
Well, okay, so
and also Turing machines are actually single-threaded even in the global multi-way case. Because there's just a single head.
Wait a minute. Okay, so e.g., so the real example here is a TM emulator. Okay, and so this is, which has both non-trivial. So basically, the full answer to this is a Turing machine is a perfectly reasonable single-threaded version of history. Okay, so there can still be meaningful time. I don't know, can there be meaningful space? The Turing machine, okay, so that's the causal graph of the Turing machine there. I think there can. I mean, I think I even looked at this in NKS, the structure of space in a Turing machine. So then my question would be, so we have this, and my question would be, oh, bug. Somebody should report this bug. Can somebody do that? Shall I do it? Somebody here could do that, please. Okay, thanks. Okay, so anyway, okay, so that is a perfectly reasonable causal graph. So now the question is, why is it the case that, so this is an additional constraint on the underlying rule to be able to force non-single threadedness. Am I correct? Jonathan, do you want to comment on that?
I agree, I think.
Okay, so the answer is there could be a single-threaded physics, but we don't seem to live there. And what other characteristics will be pulled in by single-threaded physics? You know, h bar is equal to 0. Branch space is trivial. So what? What would we, you know, I mean, the fact that there exists a rule, that the underlying rule has ambiguity, I mean, then this is telling us, which is interesting, if it's right that there's nothing, that then that is a constraint on the rule. That what is the significance of the statement the underlying rule has ambiguity in terms of causal invariance? It's an independent issue, right? I mean, you can have causal invariance in the single-threaded Turing machine case just as you can in other cases, right?
It's a somewhat independent issue. I mean, obviously, you can't have causal non-invariance in a single-threaded physics.
That's true.
But I think that's the only condition.
Right. So, okay. So, causal non-invariance is impossible in single-threaded physics. Okay.
Non-invariance.
All right. Exactly. Yes. Okay. So what? Okay. So again, let's go back to what we were trying to figure out to begin with. We're trying to figure out. This is giving us effectively. So first thing is to really thread through, which I don't completely understand. Although I've now finally, I'm excited because I think I actually understand the kind of logical structure of what goes wrong with Bell's, with this class of issues, right? But I think it would be good to tighten up which one is the right one to go for, just in terms of the technical structure of Bell, CHSH, Cauchy-Specker.
Well, I mean, CHSH is a Bell inequality. It's just the Bell inequality. Yeah, so instead of having two detector settings, or having detector settings A, B, C, you have detector settings A, B, A prime, B prime. It's a slightly different inequality, but it's the same idea. But it's the point is all of the Bell inequalities are testing the same thing, that they're all probing non-locality. And the Cauchy-Specker theorem is testing an independent thing, which is this non-contextuality.
Okay, walk me through in the case of the strings. So I'm going to guess, I might be wrong, that the non-locality thing winds up being, in the case of the strings, the statement that the size of the left-hand side of the rewrite is bounded, and that the contextuality thing ends up being the number of rules is bounded. Am I obviously wrong?
I don't understand the statement well enough to comment.
That would be my hypothesis. I mean, in other words, that yeah, by the way, Brian on the live stream is commenting on not being able to copy from a document. That wasn't the thing I was reporting actually as a bug. The thing I was reporting as a bug was that there wasn't a semicolon in the click to copy text. But the not being able to copy diagrams is unfortunately a feature, a very nasty defined feature of some operating systems and the way that they handle clipboards and the focus, the question of what windows are in focus. And we've been hunting it for ages. And it's not clear it's our fault or it may be an operating system issue, because I've actually seen it in other applications. So it's very, very obscure. Okay, well, okay.
I don't completely understand how you can have non-locality in single-threaded string systems.
Single-threaded string systems.
Because the point you're making about making the rule, effectively the size of the rules arbitrarily large is increasing the effective speed of light, but it's not introducing non-locality. Now you can have non-locality in a single-threaded hypergraph system because, as you well know, you can have edges that that don't limit to three-dimensional space.
No, there is a non-locality. The non-locality would be, look, yeah, here's the non-locality. Okay, so hold on. So this is, okay, so there's non-locality slash contextuality, so to speak.
Right.
What is it called? Contextual dependence or something? What is it called?
Just contextuality.
Okay, all right. Okay, so non-locality for strings would be a rule that picks up from different parts of the string, I think.
Mm-hmm. Right. Sure.
No, which we don't support, and or that allows, I mean, so the speed of light, look, basically the question is, I mean, we're saying that there's an infinite speed of light, and I don't know whether for these quantum mechanics results, whether infinite speed of light is equivalent to non-locality. Do you know?
Well, yeah, I mean, obviously, if the A and B detectors can propagate a signal between them instantaneously, then or back in time, as would be the case if it were genuinely superluminal, then yeah, because then the detector settings on A can fully causally determine the detector settings on B. If the
right. So I would claim that the analogy here would be not only picks up from parts of the string, but allows a left-hand side of arbitrarily great length.
Right.
Okay, and I'm claiming, what do I claim contextuality is? I mean, I'm sort of imagining, but it might be wrong, that question mark, contextuality is the use of an infinite number of a limitingly infinite number of left-hand side strings. Now, is that how?
I don't understand.
Well, you understand the idea. The question of whether that corresponds to the contextuality constraint in Cauchy-Specker, I do not know. I mean, the point here is to say, look, every different string has another, case in the rule. Do you know what I'm saying?
Right. No, yeah, I mean, so it's you're basically just saying contextuality corresponds to the case that the sequence is algorithmically irreducible.
Yes, that's what I'm saying.
Yeah, that doesn't seem implausible.
But wait a minute. So does that align with the Coach-and-Specker notion of contextuality?
Yes, well, I think so. If this general interpretation is correct, right? Because contextuality is saying effectively you can't construct a single-threaded multi-way system that describes what's going on. I think that was my starting hypothesis.
Well, right, but let's come back to
then your statement is saying that would be true if you effectively impose some computational bound. It's the same computational bound on the observer story as we've met 100 times.
Which is very exciting, that there's a connection between those things.
Right.
I mean, yes, despite your belief that it's all obvious, which it isn't to me at least. But okay, I want to just, we should wrap up soon, but I want to just loop back on what we've figured out here. I'm actually very excited by what we've figured out. It may seem trivial to you, but I don't think it's trivial, because, as I say, I think for the first time, I actually think I have an intuition for what kind of a thing these things like Bell's inequalities say. And what they're saying is, there's no way to fit the world to a single-threaded classical story. There's no way to have a deterministic theory, by which we mean a single-threaded theory, given what we observe about strings, causal graph, whatever else. But the thing that is not obvious to me, I mean, this is in a sense, yet again, the story of the distinction between in a sense, a probabilistic Turing machine and a quantum Turing machine, so to speak. Well, there's probabilistic, there's non-deterministic, there's quantum.
Mm-hmm.
And what one is saying here is that the probabilistic case is the single-threaded, but we don't necessarily know where the dice went type thing case.
Right. By the way, sorry, I just sent you a notebook about how to extend this to Bell's theorem.
Have you been figuring this out while we've been doing this? This is why. See, this is why you did you just figure this out?
I think so. So basically, okay. So what's happening here is
your multitasking capabilities are impressive. You see, this is the point. You have this is the question of single-threadedness of brains. All right, what on earth is this?
Okay, so this is a minimal model of a sort of pair production thing. So we're producing a singlet state of two particles, which are so initially XX, and so the idea is you're producing a singlet state with three possible spin directions, right? Up, right, left, whatever, separated by 60 degrees, let's say. Okay.
I can see where this is going. This is actually kind of cool, right? Okay,
yeah,
hold on. Okay, so you're saying this is the pair. X can have either A, B, or C as its outcome.
Uh-huh.
All right.
And so it's a singlet state because obviously if you just trivially, if you sum up all of the A's, B's, and C's, they will all cancel out. So the total spin is 0.
Hold on. Just save this in some reasonable place. Okay. Whoops. I'm sorry. I wasn't. All right. Do I need A, B, and C, or can I just have A and B?
Well, so the thing it depends which there are so many different versions of Bell's inequality. I think the cleanest one is the Wigner formulation, which has A, B, and C. Because you need detectors that have the measure in 3 polarization directions.
Okay.
You're measuring you have your Stern-Gerlach setup, and you're measuring spins in 3 different directions. It's separated by 60 degrees. That's the simplest case that I know.
Okay. All right. Well, we should be able to see from this. If you're right, we should be able to see how it degenerates in the case of 2, for instance.
Right.
Okay,
This
so you're
isn't
saying
this isn't the complete story, by the way. This is just the start, I should mention. So so what we're saying here is, yeah, so we're producing these two particles that have different spins, and we know that the overall state is a singlet state, because obviously if you summed up all the A's, B's, and C's, there would be equal numbers of each. So this total spin is 0.
okay.
Right. So then what we want to say is we get all of the states on the last step, and then we imagine measuring them with respect to different polarization directions. So we get our detectors and we measure each state with respect to polarization direction A, B, or C. And obviously if we measure in direction A and it is A, then we get a value of 1. If we measure in B or C, we get a value of -0.5, because we're doing a dot product with an angle of 60 degrees.
Fine. Yep.
And so then if you scroll down, you'll see the simulated detector results for the pre-completed system in 3 different polarization directions.
These are the outcomes that you get for each of these BA, AB, whatever.
Right.
Yes.
So then the question is,
although given this setup, there's just an enumeration of strings here. There's nothing. The multi-way system, we could throw away the multi-way system at this point.
Yeah, sure. As with so many things, it only becomes interesting post-completion.
Okay.
So then if we actually simulate these measurements by doing the completion procedure, we get a much more complicated multi-way system. And actually, the reason I say this is not complete is because to do this properly and to get actual quantitative violation, we need to count the path weights, because it's not the thing that matters is not just the number, the set of states, but actually how many ways of getting there are. So then these would be the simulated detector results. So then if we do that for the path weights thing, that will give us the value of the correlation functions for A, B, AC, BC. And then the statement of Bell's theorem would be exactly the statement that we could not have reproduced those same path weights, we could not have reproduced the same states with the same set of multiplicities that would therefore produce the same detector results with a single-threaded multi-way system.
Okay, now notice that multiplicities aren't a creature of single-threaded multi-way systems.
Right, so you need to get, there's multiplicity of states. That's what you'd need to simulate. You'd need to basically claim that you could unroll this whole big complicated multi-way system into a single thread with multiplicities.
How would you get the multiplicity in a single-threaded case?
Well, in the same way that you were talking about earlier, if you had 2 poles of the same length, but then they're allowed to, you're allowed to have repeats.
Yeah.
Then you get multiplicities of states, even though you don't get multiplicities of events. And in fact, wait, no, in a single thread you can get multiplicities of events. That's what's happening in the A's case.
Right.
So actually, this is a bit more complicated.
Yes. Right. So right, there are multiple paths there. The A's. So in your case here, you're saying that there are multiple outcomes. I see. So the issue would be, in your picture, there are multiple outcomes, but you have a multi-way system that effectively just is like an octopus with tentacles, so to speak. But the tentacles don't branch and rejoin and so on.
Right.
Okay, so you're saying I think this is going to degenerate into this simpler case, but I mean, in the Bell's...
It may well do, in which case we'll have discovered a previously unknown connection between Bell and Koch and Becker. Right.
Okay, so the Bell's case, the issue is, do you have to have a branching, merging multi-way system for your different outcomes, or can you have a quotes pure octopus, i.e. a thing, i.e. something where each outcome is just a separate branch, and where there's no need for what one would say quantum mechanically is entanglement and interference and so on, right? So
Right.
this is asking, I'm very impressed that you can multitask and produce this at the same time as having this other conversation. Although I think sometimes you sound like you just don't believe anything I say, when in fact you're of multitasking and doing something completely different. Okay. Anyway, never mind.
Sorry.
That's all right. Okay. But okay, so again, let's loop back. So the key idea is to use our extremely granular notion of a multi-way system to address what would otherwise have to be done in terms of God knows what C-star algebras and so on.
Mm-hmm.
And in our case, what would normally be an arbitrary operator becomes just a particular hypergraph rewrite or a particular string rewrite.
Mm.
And so, and because we have another thing going for us, which is that we can actually imagine enumerating all possible string rewriting rules.
Mm-hmm.
So, you see, one of the things that I'm curious about, and coming back to this thing that up here with strings, you know, how unusual is it? In other words, what are the special features of the cases where there is a single-threaded interpretation of a string sequence? You know, in other words, what level of triviality does that have to have? There's a certain kind of reducibility that's necessary to achieve that.
Mm-hmm.
How trivial does it have to be?
Right, right. Is it incorrect to think of that as an algorithmic randomness bound?
No, it's not completely incorrect to think of that. I think it's a question. I mean, it's one of these things of saying, look, for example, you know, certain kinds of things are purely periodic, certain kinds of things are nested. This is a certain kind of regularity that must exist in the sequence of strings so that it has the property. So one question would be, is that regularity a readily recognizable regularity? Just like, for example, periodicity is what you might characterize as a regularly recognizable, an easily recognizable regularity. So in other words, in this case, you know, the question would be, is there an easily recognizable regularity of every string sequence, of any string sequence that is, quotes, ST explainable?
That's a cool name for a complexity class.
Yes. The suggestion that that you, Jonathan, be the code writing person here, which is yeah, we really
that would be
need
way too much pressure.
What we really need is young Christopher. He's the fastest at these at just spinning code, except that apparently people are suggesting that we have some kind of multi-stream, like a multi-way system to and then see whether we have causal invariance at the end. Go ahead.
Bring on collaborative notebooks.
Yeah, that might work. It might work.
That could be fun.
It might work. It might also be just utterly confusing. We could actually do with streaming, with the streaming notebook technology, we could actually do some of that. I'm not sure if it would be. It might be. You know, honestly, the world of multi-way systems can get pretty hard to understand pretty quickly. And I think that's what we might end up with, is in a multi-threaded, multi-way notebook environment. But okay, we should probably wrap up here. But I'm actually very pleased with this. I think that the in a way that I'd never understood before, this is kind of the nub of what's happening in these various kinds of yeah, Richard on a live stream is saying it'd be nice to see the notebooks updating locally. We should be able to. We actually have a technology now for streaming notebooks out. It's not quite production ready, but it should be so that everybody could have their own copy of this, and they would this copy, the copy that they would see on their machine would be non-editable, but they could always copy any piece of it into a separate notebook to do further computations. And that would be, then we could have a truly multi-threaded, because there are lots of people here who I think are figuring out all kinds of interesting things on our live stream, and then we could really have that would be a great form of collaboration. You know, we've been trying at our summer school, we've been trying to do really multi-threaded kinds of collaboration like that for a number of years, and hopefully this year we will finally. This year, of course, we hope to have several very interesting technical innovations. I mean, this is the first and only time so far that we've done a remote virtual summer school, and we hope we'll have some really very interesting technical things to show for how that kind of event can be done. All right. Okay. This actually went a lot. This was great as far as I'm concerned, because, as I say, the nub of what's going on, I think I really understand in a way that I've never understood before. And I'd like to make more closer connections to what the formalism of Cochran, Becker, and Bell and so on. But I think that the conceptual point is now rather clear, which is wonderful. Okay, I am being told to remind people that tomorrow I am signed up to do another science and technology Q&A for kids, which is always fun. Much lower stress than this, I have to say. And the topic tomorrow is about things that show up in science fiction, and can they be real or not? And I have to say that I have been starting to think about the whole faster than light travel question in our models, and the different meanings of faster than light travel, and how much stuff you have. So anyway, lots of, and this concept of higher dimensional space tunnels and so on. It will be truly remarkable if it turned out that there is a mechanism in our universe to, for example, create a space tunnel, but that they do not occur naturally. I mean, in other words, it's like there exist things that, well, for example, radioactive elements are something which we can create. Anyway, I'm starting to talk about a completely different subject, but we can create, and they exist in supernovas and things like that, but they do not sort of generally hang around. They're not things you can just find in the universe usually. And so the question is, if it is possible to have, for example, space tunnels, is there a way, could one even imagine a way to create them by, colliding 4 black holes in just the right way or something? And I mean, actually, okay, so now I'm going to ask one question here, but I mean, can we imagine in our models, we haven't, yesterday we were looking at black hole formation. We have not looked at black hole interactions and what kinds of weird things can happen in, could there be, for example, I think the main thing that will happen in our models is something very undesirable. It's kind of the ultimate exile mechanism, is, that piece of the universe can actually tear off, which is something that is not common, that one doesn't really think about in standard general relativity. And I have a feeling that a lot of these sort of weird collisions between black holes will lead to tearing off pieces of the universe, which is kind of not really what you want if you're looking for travel, so to speak. That's called you go on the that's a one-way form of travel. I don't know. Jonathan has a final comment here. Do you have any? Do you
Exciting
have any?
idea.
Right. But the question is, look, I think in the end that we're going to be stuck. Here's what I predict is going to happen. We will not be able to show that space tunnels are impossible. We will not be able to show that there are singularity theorems that imply that they're, just like there is some inevitability. We sort of understand the inevitability of the singularity theorems leading to black holes, but the suggestion that there might be a theorem that says you can't spontaneously create a space tunnel is kind of I predict that we will not be able to find such a theorem, but that we will also not be able to show that it'll be basically undecidable whether you get a space tunnel that persists for a given amount. In other words, to know whether you can have a persistent space tunnel will be undecidable, but you may be able to create what you might call an apparent space tunnel that lasts for a certain finite time. And it may be, the bad case. And now I'm amusing myself with the speculation. I mean, in the bad cases, you have a space tunnel, but it's essentially undecidable whether you'll make it to the other side of the space tunnel. So, in other words, it's a high risk proposition. If you're going to travel by a space tunnel, that that it's not. Anyway, okay, just for fun. Okay. Great. All right. Well, thanks very much. This was great. And all right, let's wrap it up and look forward to seeing people on another live stream another time. And I just want to remind everybody that the summer school is coming up. If you're interested in this stuff and you want to be sort of seriously involved, come to the summer school. And I think we're going to get sort of the there will come out of the summer school lots of important papers about what's possible with this perspective on physics. Anyway, thanks, and see you all later. Bye.